This
అయ్యి
conference will
మీరైతే
now be
కనిపించడం
recorded.
లేదు.
కనిపించలేదు. ఓకే.
మీరు కనిపించడం లేదు. ఓకే సార్.
This conference will now be recorded. This conference will now be recorded.
Okay. Good morning, students. So previous class, so we are listening the pulse and digital circuits first unit, linear wave shaping. So what is meant by linear wave shaping? So linear wave shaping is nothing but linear elements, what are the resistor and capacitor or inductor, these circuits we are applying non-sinusoidal signal, then output waveform shape will be changes. Output waveform shape will be changes. Now we are going to the non-linear wave shaping circuits. Within this one, we are using the circuit elements are non-linear elements and passive elements, RLC. So these RLC circuits, so RLC and non-linear device like diodes or transistors, you are using the circuit non-linear circuit element. Now you are applying sinusoidal input, then output you are getting as a non-sinusoidal waveform. So the process of producing non-sinusoidal output waveform from sinusoidal input using non-linear elements, then this process is called as non-linear wave shaping circuits. So within this one, according to J into Kakinada syllabus is, in the second unit is non-linear wave shaping. So first will be diode, clippers, transistor. How it will be diode will be operating as a clipping operation by using diodes and resistors. And similarly, how it will be transistor operating as a clipping device. Similarly, by using more number of diodes, that means 2 diodes you are using. So how it will be input waveform, sinusoidal waveform, how it will be clipping in the 2 levels. Then after transfer capacities of clipping circuits. Then after another one by using 2 transistors, how it will be clipping of the input sinusoidal waveform at the 2 levels. These are the all are be clipping part. Because in the non-linear wave shaping, it will mainly be classification of 2 types. One is the clippers, second one is the clampers. Now we are moving to the clamping operations. Within this one, you are using non-linear device and passive components. Mainly, are using here capacitor. So why you are using capacitor here means whenever any of the sinusoidal waveform and DC waveform both will be transmitting to the any of the capacitor circuit, then some amount of DC will be voltage will be blocked by the capacitor. Now addition of the DC voltage by using here will be capacitor. That means the DC level of the input waveform will be either shifting upward direction or downward direction of the input waveform. That is the clamping operation. So different types of clamping circuits, positive peak clamping and negative peak clamping. Then after, clamping circuit theorem. So what is the practical clamping circuits and effect of diode characteristics on the clamping voltage and transfer characteristic clamper. This is the syllabus of the J into Kakinada second unit syllabus of the pulse and digital circuits. So now we are going to the, what is the, already I explained this diagram. This network, non-linear network contains by the active elements and simultaneously. So active elements means here you are considering the RLC component passive elements, and another one you are considering the non-linear elements, diodes and transistors. So these combination formed by the network or circuit is called as non-linear wave shaping network or circuit. Now you are applying sinusoidal input, output waveform is non-sinusoidal waveform you are getting. So previously in the linear wave shaping you got only non-sinusoidal signal as the input, output waveform is waveform shape will be changes. Now coming to the, what are the types of the non-linear wave shaping circuit? There are the 2 types. One is the clippers, second one is the clampers. So this non-linear network consisting, already I told that linear elements and non-linear elements. Linear elements are RLC, resistors, inductors and capacitors. Similarly, non-linear elements are, include transistors, diodes and vacuum tubes, etc. Here mainly are using diodes plays very important role in the non-linear wave shaping circuits. And next one, what is meant by clipping? So clipping means you have to remove some portion of the input signal. Let us example you are considering off-wire rectifier. You have seen the off-wire rectifier you have done in the experiment in the EDC lab. So within this one, input is a sinusoidal waveform. Output you want will be pulsating DC, only positive peaks you are getting. Similar, that meaning is input is sinusoidal waveform, some part of the input waveform. That means off-wire rectifier example is negative peak of the input waveform will be removed one. there is a desired portion you want to transmit. So clipping circuit is nothing but, so remove the unwanted part of the signal and transmit only, so whatever the requirement part of the input signal you want to transmit. And clipping circuits are the different names will be there. So one is the voltage limiters or current limiters or amplitude limiters or selectors or slicers. They are the different names for clippers depending on the application. Next one, generally these types of clippers are mainly will be series clippers and shunt clippers. How can say that this is a series clipper or shunt clippers means depending on the diode connection between the input and output, how to be connection diode. So clipping circuits mainly you are using the diodes or transistor will be non-linear elements, and the additional one is linear element resistor. And next one, so clippers are perform the two operations mainly. One is altering the shape of the input waveform or otherwise protecting circuits from transient responses. So basically clipping can be achieved by simple off-rectifier configuration. So rectifiers, nothing, the rectifier circuit is will be series clippers. So generally what is the rectifier operation is? So alternating voltage, that means AC is converting to pulsating DC. So clipping circuits can be used to protect sensitive circuits from the effects of transients. There are the three different topologies of clipping circuits, which are a series in a clipping circuit with a combination of diode, resistor, and a reference voltage. A circuit consisting of more number of diodes, resistors, and reference voltages. So first one is either be single diode, resistor, and reference voltage they are utilizing, either be series or parallel combination. And second one is circuit consisting of more number of diodes. That means two diodes they are using by using resistors and reference voltages. And next one is by using two transistors, how the clipping operation be done. That circuit is called as emitter coupled differential amplifier circuit. And next one, this is a clipping circuit. Generally, non-linear device you are using the diode. So we know that VI characteristics of the diode in the already ED segments you have done already. So in the first quadrant you are considering is VI characteristic forward bias condition. Similarly, third quadrant you are reading is in the reverse bias condition. And similarly, B diagram here indicates that ideal diode constraint. So ideal diode will be cut-in voltage will be 0 and forward resistance will be 0 and reverse resistance will be infinity reverse bias resistance. Similarly, in the practical case, V gamma is considered, cut-in voltage will be considered, and forward resistance and reverse resistance will be ideal values will be considered. Similarly, practical one, V gamma is some finite value, and forward resistance also some finite value between 10 ohms to 100 ohms. Similarly, reverse bias resistance is considered infinity. So in that condition, how will be graph will be there. Similarly, last one practical case. And now diode will be this non-operation mainly are using will be switch. Where is the when will the switch will be operated in the diode? So everybody knows that diode will be forward bias condition in the closed condition. Closed act as a closed switch. That means what are the anode and cathode simply will be short circuited. And zero forward resistance. RF value will be 0 in the ideal case. Whenever we diode in the reverse bias condition, it acts as a open state of the switch having infinite resistance. That means reverse bias resistance ideal case will be RR equal to infinity. This is the equivalent circuits open switch and closed switch. And next one, another one. This is the VA characteristic of ideal diode. So ideal diode in the you have to update the first diagram. So here will be open switch. So open switch means so whenever will be reverse bias condition, negative supply voltage connected to the diode, then will be open switch act as open switch. Whenever will be forward bias condition, positive voltage applying to the diode forward bias condition, this diode will act as a closed condition, closed switch. Similarly, we can show the silicon diode. So how it will be open switch in the reverse bias condition and forward bias condition, cut-in voltage V gamma also will be anchored. V gamma is nothing but here will be for silicon generally considering 0.7 volts. And RF will be generally very small value neglect one. That is a closed switch indicator. And similarly, VA characteristics, similarly germanium diode in the reverse bias condition and forward bias condition, cut-in voltage will be so 0.3 volts will be considered. And next come to the series clippers. So series clippers having so generally we can say there are the four types you are considering. One will be reference voltage will be 0 or positive reference voltage will be considering. So first of all, you are going to the negative peak clippers. So what is meant by negative peak clipper circuit diagram? You have to see the diagram, this diagram. So what is it meant by this series? Here will be this positive, this input one you are connecting positive terminal, Similarly, output one also with this resistor one end will be positive terminal. So in between input and output, diode is connected in the series connection. In between input and output, diode is connected. That is called as series connection. Next one, the output will be taken here will be across the resistor. So now what is meant by the transfer characteristic? So previously a VI characteristics graph comes in x-axis will be voltage and y-axis will be current will be taken. Now here considering is input voltage and output voltage. Input voltage and output voltage. The graph is called as transfer characteristic curve. You have to see this one transfer characteristic curve. So x-axis will be VI and y-axis will be V0. And now what is this diagram? This is the output waveform. Input waveform is sinusoidal waveform. There is a positive peak and negative peak, both will be contained. Now here will be what is the reference voltage? Here will be resistor, other end will be connected to ground. Now here will be reference voltage nothing but 0 volts. Now input voltage VI. So input voltage VI is less than 0. So less than 0 means negative peak. So once you are applying negative peak, so input of the diode will be connecting the negative peak. That's why diode will be reverse bias. So reverse bias means diode will be off state, that means open switch. So once it will be open switch, then what is the equivalent diagram? So in equivalent circuit diagram is open switch condition, this diode will be replaced by simply open circuit. So once it will be open circuit, then input is not transferred to the output. So output voltage across the resistor will be 0. So that's why you have to observe here output waveform, negative peak waveform, output waveform with dotted line. That means output waveform value will be 0 for negative peak of the input case. Similarly, this transfer characteristic curve also output voltage waveform will be 0. That means the slope equal to 0. Next one, now you are applying input is positive peak. So once you are applying positive peak, what will happen? This diode will be forward bias condition, act as a closed switch. This is ideal condition. We have shown this condition. For VI is greater than 0, diode will be on condition, act as a short circuit. Then whatever input will be there, the same input is transferred to the output. We are assuming here it will be diode forward resistance RF will be very small or negligible, almost equal to 0. In that condition, so VI. Now V not equal to VI means slope equal to 1. That means in the positive peak condition of the input waveform, so same input is transferred to the output, V not equal to VI, slope equal to 1. Now observe the output waveform is only positive peaks. So same procedure you observed in the off-pair rectifier also. So here will be negative peak will be clipped off. So only positive peaks will be transmitted. And next one, negative peak clipping circuits. It will be transferred only positive amplitude of the portion and negative amplitude will be clipped off. This is called as negative peak clipping circuit. So next we are moving to the positive peak clipper circuit. So previous circuit and this circuit, what is the difference? You observe it. Previous circuit here will be diode will be forward bias condition. Now you are considering diode will be reverse bias direction. Now you are applying sinusoidal waveform. Now you are applying this sinusoidal waveform. Input waveform is comparing with two levels. What are the two levels here? Ground level. Because no reference voltage I am assuming is VR equal to 0. So that's why for two conditions, VI is less than 0 condition and VI is greater than 0 condition. That means input voltage is less than 0, input voltage greater than 0. These are the two conditions to be considered. So first condition, so VI less than 0 condition. That means input is negative peak. So once it will be negative peak will be applying as the input waveform, then diode will be reverse bias. Now diode will be on condition. So on condition means diode acts as a simply short circuit. So once it will be short circuit, then whatever input waveform, negative peak waveform is transferred to the output. Now output voltage across the resistor equal to V naught equal to VI. In the case of negative peak, you are applying. Now you are applying positive peak. That means positive peak means VI is greater than 0 condition. So VI greater than 0 condition. So positive voltage. That means diode cathode terminal will be more positive compared to the anode voltage. That's why diode will be reverse bias condition. Diode will be off condition. We are using ideal diode. That's why positive peak you are applying, this diode will be open circuit. So once it will be open circuit, here the input is not transferred to the output. So output will be 0. So that's why for VI greater than 0 condition, so diode will be off condition, open circuit, output voltage will be 0. So according to these conditions, you have to draw the transfer characteristic curve also. So transfer characteristic curve you observe here. This is the diagram. This diagram, x-axis will be input voltage, y-axis will be output voltage. So right hand side, this is the positive voltage and this is the negative voltage, negative peak values. In the negative peak values will be diode will be on condition, slope equal to 1, V not equal to VA condition. That's why negative peak will be transmitted as a output waveform. Input waveform and output waveform for the case of negative peak will be same. For the positive peak condition, so that means input is positive voltage, VA greater than 0 condition. So diode will be off condition. Once the diode will be off condition, you have to see this diagram. Input will be is not transferred to the output. So output voltage will be 0. So once the output will be 0, then automatically slope equal to 0. So positive peak output waveform value will be V not equal to 0. This is the how it will be positive peak will be removing from the input sinusoidal waveform. And next one, another one is this is the reference voltage with 0 we consider. One is the two circuits you have seen. One is the negative peak clipping circuits like a half rectifier circuit. Similarly, positive peak clipping circuit here will be diode will be reverse bias condition. And next we are moving to the another type, clipping below the reference voltage. So here will be diode will be connected in the series connection and reference voltage will be positive reference plus VR voltage. Generally, let us example in input sinusoidal from plus 5 volts the peak value, positive peak value, and the negative peak value is minus 5 volts. I'm taking let us example VR equal to 3 volts. Now, what are the conditions that comes from this one? Previous one will be two conditions. What are the two conditions? The reference voltage will be 0 here. That's why VI less than 0 and VI greater than 0 will be considered. But now here will be what are the conditions we consider here? So VI less than VR and VI greater than VR. They are the two conditions. Now first condition is VI less than VR condition. So VI less than VR condition, what about the diode? You have to see this diagram. So VI less than VR. Let us example VI is 0 to 3 volts. Actual peak value is 5 volts. VR equal to 3 volts. That means input voltage lies between 0 to 3 volts. Here will be diode positive terminal or anode terminal will be less voltage compared to cathode. So here will be 3 volts. Here will be less than 3 volts. Now diode will be off condition. Now diode will be off condition in the circuit will be open circuit. So once it will open circuit, then output voltage across the resistor reference voltage. Output voltage equal to V not equal to VR. So that's why you have to see the diagram. Input voltage less than reference voltage, then diode will be off condition. So V naught is parallel to the VR. So output voltage equal to VR only. And next one, input voltage, this condition, this line is called as less than VR voltage. Next second condition, whenever VA is greater than VR, input voltage greater than reference voltage. Input voltage greater than reference voltage means you have to see this one. That is example VR equal to 3 volts. Here will be 3 volts and positive side anode will be 5 volts. So here will be 5 diode anode side and this one is 3 volts. Diode will be forward bias condition. Forward bias condition means the diode acts as a closed switch. So once it will be closed switch and act as a short circuit, likewise this equivalent circuit. Now input waveform, whatever input waveform above reference voltage, same waveform will be transferred to the output. So that's why whenever input voltage greater than reference voltage, diode will be on condition, input voltage transferred to the output. In that condition, so V not equal to VI, V not equal to VI condition. Slope equal to 1. You have to see this slope is equal to 1 whenever input voltage greater than VR reference voltage. This actually VI, not T. This is a VI. This is the output voltage. Input voltage x-axis, output voltage will be y-axis to consider. These are the two conditions. Corresponding will be output waveform shown here, and similar this is the transfer characteristic curve. So you have to indicate this one also. This is the green line is nothing but so input voltage less than reference voltage condition. So less than reference voltage condition, diode will be off condition. So diode will be off condition means output voltage V not equal to VR. So whenever input voltage greater than reference voltage, input is transferred to the output, diode will be short circuit. So slope equal to 1 condition. Now see the output waveform. This is the output waveform will be shown. This is the transfer characteristic. Next one, this is the fourth circuit, clipping above the reference voltage. So previous circuit and this circuit, what is the difference? Clipping below the reference voltage and clipping above the reference. You have to see this one, clipping below the reference voltage, diode is connected in the forward bias direction. But clipping above the reference one, you have to see the diagram. Clipping above the reference, diode is connected in the reverse bias direction. Now, what are the conditions will be considered? Again, there will be two conditions. What are the two conditions? Vi is less than VR condition and Vi greater than VR condition. These two conditions, what is the diode status? Either on or off condition, and corresponding output values you have to note down. So first condition I am considering case 1. So whenever will be Vi is less than VR condition. So whenever Vi less than VR condition, what about the diode? See this one. So input voltage less than the reference voltage. That means diode anode terminal will be positive voltage, more positive voltage compared to input voltage. So automatically diode will be on condition. On condition act as a short circuit. So in that condition, input will be transferred to the output whenever Vi less than VR condition. This is the first case. So Vi less than VR condition. So input is transferred to the output condition. That means V not equal to Vi. So you have to observe this diagram output waveform. This line is the VR reference line. This reference line below input waveform. So V not equal to Vi. Diode will be short circuit. Whenever so Vi greater than VR condition, we are moving to the second case. So second case will be Vi is greater than VR condition. So Vi greater than VR condition. Whatever the diode status, you have to see this one. Vi is greater than reference voltage. That means diode cathode terminal is more positive voltage compared to anode. So diode will be off condition. So here will be, let us example 5 volts, here will be 3 volts. Diode will be off condition. So once will be diode will be off condition, what is equivalent circuit? This is the equivalent circuit. Now input voltage Vi greater than reference voltage, diode act as a open off state, that means open switch. Then V not equal to VR because output voltage parallel to the reference voltage VR. Now input waveform greater than VR reference voltage, then output waveform value equal to V not equal to VR. That's why it will be above waveform be clipped off above the reference level. VR reference level above the input waveform be clipping. This circuit is called as clipping above the reference voltage. And this is called as transfer characteristic curve. The x-axis will be input voltage and y-axis will be output voltage. So whenever we diode will be on condition, V not equal to Vi. Whenever we diode will be off condition, so V not equal to Vi is greater than VR, then diode will be off state. That means slope equal to 0, output equal to 0. Output voltage equal to VR. So if that condition, slope equal to 0 condition. And now you are seeing up to now series clippers. That means between input and output, this input one, this output, and in between diode is connected in the series connection. Without reference and with reference, you have seen positive references. And similarly, negative reference also will be there. And do it similarly. Now I am moving to the shunt clippers. So shunt clippers means diode will be connecting across the shunt connection. You have to see this diagram. This is a shunt clipping example diagram. So first one is positive peak clippers. So positive clippers means you have to see the diode in the shunt connection in the forward direction, forward bias direction. Now again, input waveform Vi is contains sinusoidal waveform, both positive peaks and negative peaks. Now what is the reference voltage here in this condition? 0 reference voltage. Now conditions are Vi less than 0 condition and Vi greater than 0 condition. So first condition, Vi is less than 0 condition. That means negative peak or positive peak. So Vi less than 0 means negative peak. So once you have a negative peak you are applying at the input side, now diode will be, what will happen? So diode will be off condition. So why? Because here will be negative input will be coming in the diode anode terminal and cathode is 0. So 0 voltage value is more positive compared to negative voltage. That's why it will be, so diode will be off condition. So diode will be off condition. This will act as a, this will be open circuit. Then will be negative peak condition. So output voltage value will be 0. Similarly, whenever Vi value is greater than 0, positive peak you are applying. So positive peak you are applying means diode will be forward bias, act as a short circuit. So once it will be short circuit, output voltage across the short circuit means 0. This the reverse will be there. So V not equal to the reverse one. Now output waveform you have to see. This is the output waveform for positive peak clipping circuit diagrams. And next one, another one, negative peak clipping circuit. So here will be diode will be reverse bias direction. Previous one will be diode will forward bias direction. Now will be reverse bias direction. Again, will be two conditions. What are the two conditions? VI less than 0 condition. That means input voltage less than the reference voltage. That means negative peak. And similarly, VI is greater than 0 means positive peak you are applying. So now these two conditions, what is the output voltage values? So first will be VI less than 0. That means input is negative peak you are applying. So negative peak you are applying means here will be input is negative peak coming this direction. So diode will be on condition. This is also reverse bias. Input is reverse negative voltage. So diode will be on condition means act as a short circuit. Once it will be short circuit, then output voltage across the short circuit is 0. And next one, slope equal to how much will be there? In the slope equal to this short circuit will be 0. And next one, whenever VI is greater than 0 condition. So VI greater than 0 means positive peak. So positive peak applying diode will be reverse bias condition, off condition. So once it be off condition, so whatever input is there, same input is transferred to the output. And similarly, next one, by using reference voltage, clipping below the reference voltage. Now will be diode will be reverse bias condition. Here will be plus VR reference voltage applying. Now what are the conditions to be considered here? There are the two conditions. One is a VI less than VR condition. Second condition is VI greater than VR condition. So first condition, VI less than reference voltage condition. So what is the diode operation? Either be closed switch or open switch because they are assuming ideal diode. So for that conditions, how to operate it? You have to see this one, VI less than VR. So VR is nothing but positive reference. You have to see this one. This is the input sinusoidal waveform, positive peak and negative peak. This is the reference voltage. So positive reference voltage. Now let us example this VR equal to 3 volts. Now peak value is 5 volts and negative peak is minus 5 volts. So 3 volts reference voltage below the input waveform. Below the input waveform. Now what about the diode status? So diode will be less than 3 volts reference voltage. Diode will be on condition. Diode will be off. Will be VR is positive voltage and diode negative less voltage. Diode will be on condition. Once it will be diode will be on condition, this will act as a short circuit and V0 is parallel to VR. So that's why input voltage is less than reference voltage. Diode will be forward bias. Output voltage V0 equal to VR. So for this condition, slope equal to 0. And next second case, VI is greater than reference voltage. Let us example reference voltage are assuming 3 volts. Input voltage is 5 volts peak value. So in between 3 to 5 input voltage. That means here will be positive voltage, more positive. Let us example 5 volts. Here will be 3 volts. So diode will be off condition. So once it be diode will be off condition, the equivalent circuit this one. So diode will be off condition. What will happen? This VR is inactive one now. Now whatever input is there, same input is transferred to the resistor and output. That's why output waveform will be above VR reference voltage is same as input waveform. V not equal to Vi. So at this time, slope equal to 1. This is a transfer characteristic curve and this is the output waveform. Here you have to indicate reference voltage VR. This is the peak value. This is the clipping below the reference voltage. Diode will be reverse bias connection, positive reference. Now another circuit, clipping above the reference. So clipping above the reference level. See this one, diode direction. Previous will be reverse bias direction, now will be forward bias direction. Now again will be two conditions. What are the two conditions? Vi less than VR case. Second case is Vi greater than VR condition. So first condition, Vi less than VR condition. Input voltage less than the reference voltage condition. This is the reference voltage VR line below the input waveform. Then what will happen? See, let us example VR equal to 3 volts. Here will be input waveform is less than 3 volts. So less than 3 volts means diode will be positive side or anode side will be less than 3 volts. Negative side, cathode side will be more positive, 3 volts here. So diode will be reverse bias. That means off condition. So once it be diode will be off condition, what will happen? This VR reference voltage be inactive one. Now will be Vi is input is transferred through resistor and output. Now V not equal to Vi. Whenever will be Vi less than VR condition, Vi equal to V naught. Both will be same. So for the same condition, you have to see this one, slope of the negative peak to up to input voltage VR, reference voltage, V naught equal to Vi, slope equal to 1. Within this portion, input and output equal to same. That is input waveform up to VI equal to VR, reference voltage below, output waveform and input waveform both are the same. Whenever input voltage VI is greater than VR, that is the second case. Now second case means here will be diode anode will be more positive, in between 3 to 5 volts. Here will be only 3 volts. So diode will be forward bias condition. Forward bias condition means this will act as a short circuit. You have to say this one, short circuit. So once it will be short circuit, now output voltage parallel to reference voltage VR. That means input voltage Vi greater than VR condition, output voltage V not equal to VR, slope equal to 0. So output voltage V not equal to VR condition. This is a clipping above the reference voltage. VR reference voltage above the input waveform will be clipped off. These are the 4 types of shunt clippers. So you are considering reference voltage 0 and reference voltage positive references. You are considering. These are the 4 types you have seen in the shunt clippers and series clippers also. And next one more important one. How many circuit diagrams will there? I told that in the series will be 4 circuit diagrams. Reference voltage will be 0, and similarly reference voltage positive reference. So series will be 4 and shunt will be 4. But one more thing also, negative reference supply also will be there. Then will be here considering this is the positive reference. Here considering minus supply, minus VR also. Then another circuit. Likewise will be series clippers will be 6 circuits and shunt clippers will be 6 circuits will comes. So corresponding outputs and transfer characteristics we have to shown here. Go through this one. And now another important circuit diagram is clipping at 2 independent levels. This is a very important circuit diagram because here more number of diodes. That means 2 diodes and 2 reference voltage will be constrained. So one is the diode forward bias direction. Your positive reference voltage VR1 you constrained. Similarly, diode will be reverse bias direction. So applying negative supply reference voltage. So for this condition, input sinusoidal waveform we are applying here. Then what is the output waveform? This waveform or the circuit is called as sine wave to square waveform conversion. By proper values of choosing reference voltage VR1 and VR2, both will be same, and frequency also will be small, will be constrained. Then how to be high frequency will be constrained. Then will be the sine wave is converting to square wave. That is a 2-level clipping circuit. This is one of the important one. So here will be how many conditions will come, or how many cases will comes here. So previous one reference voltage either 0 or reference voltage VR. Now here will be 2 reference voltages. VR1 positive reference voltage and minus VR2 negative reference, 2 reference levels. So that's why. So total input waveform divided into 3 parts. So one is a Vi greater than VR1 condition. Next one is in between minus negative reference voltage minus VR2 to positive reference voltage. That is the Vi lies between these 2 reference voltages. Similarly, Vi less than minus VR2 negative reference voltage. So these 3 conditions, what is the diode status? Let's say the D1 or D2 will be on or off conditions, and corresponding what is the output values. So you have to see this diagram, how it will be operation will be going on. They are the different conditions. See here, it is a combination of positive shunt clipper and so negative shunt clipper. So within this one, how it will be operation? First condition will be Vi is greater than VR1. That means input voltage greater than reference voltage VR1, positive reference voltage. So now this diode will be forward bias D1 because diode D1 is this the input voltage greater than VR1. Let us example VR1 equal to 3 volts. Input is between 3 to 5 volts. Positive peak is 5 volts. Peak value maximum. So in between 3 to 5, here will be, let us example 4 volts. So here will be 3 volts, here will be 4. So diode will be forward bias condition D1. So this will act as a short circuit. Or come to the second one. What about the D2? So D2 here will be positive voltage. Let us example 4 volts. So here will be here getting minus VR2. Minus VR2, let us example minus 2 volts. This is the minus 2 volts, this is the plus 4 volts. Then diode will be D2 will be reverse bias. D2 will be off condition. So D2 will be off condition. D1 is on condition whenever input voltage is greater than VR1. For this condition, now what is the output voltage value? So now minus VR2 supply voltage will be inactive one. So V0 is parallel to VR1. So here output voltage equal to VR1 whenever condition is Vi greater than VR1. And next one, come to the second condition. So whenever Vi is less than minus VR2 condition. That means input voltage less than minus VR2 condition. For example, minus VR2 means minus 2 volts. That means input voltage lies between minus 2 volts to minus 5 volts. That is the example I am taken is minus 3 volts. So minus 3 volts will come in this direction. Minus 3 or minus 4. In between you cannot take any value. Minus 2. This value is minus 2 volts. Minus 2 less than this value means minus 3 volts, minus 4 volts, minus 5 volts. That is the example I am taken minus 4 volts. So minus 4 volts means D2 will be on condition. Let us see this one. This is a minus 4 volts. This is a minus 2. So minus 4 here. This is a minus 2. So minus 2 is larger value compared to minus 4. So diode D2 is forward bias condition. Diode D2 is on condition. And same minus 4 volts here. And this one is plus 3 volts. Now this side will be off condition. D2 is on condition. D1 is off condition. Now this is the second condition. You have to see this one. Now for this condition, now D2 is on condition at a short circuit, D1 is off condition, VR1 is inactive one. Now output voltage is parallel to minus VR2. That means input voltage lies between minus VR2 to whatever the peak values in between. That means less than minus VR2. Then output voltage is equal to minus VR2. And last third condition, whenever input voltage lies between minus VR2 to plus VR1. See this one. This is the minus VR2 line. That is the example minus 2 volts. VR1 is 3 volts in between. So minus 2 volts to plus 3 volts. In between, what is the diode operation say? The D1 or D2, which one will be on and which one will be off condition? Or to check. Let us example minus 2 to 3 volts. In between, I am taking let us example input is 2 volts. First voltage. Now coming here, 2 volts is direction. Now diode will be D2 is reverse bias direction. Here will be 2 volts. So here will be minus 2 volts. Now this is a minus 2 means less voltage compared to cathode. Anode is less voltage. Diode D2 will be off condition. Similar here, the same 2 volts will be here, but here will be 3 volts. So this D1 also will be off condition. Both diodes will be off condition, and our input voltage lies between minus VR2 to plus VR1. In between voltage, both diodes will be off condition. This is a very important one, because input voltage lies between two reference voltages in between. Then both diodes will be off condition for any two-level clipping circuit. Then these reference voltage will be inactive. VR1 and VR2 will be inactive. Then input voltage transferred to the output V0 equal to Vi. Now observe the output waveform also. Input waveform lies between minus VR2 to plus VR1. Input and output waveform both will be same. So within the same, then transfer characteristic curve also will be slope equal to 1. And less than input voltage less than minus VR2 and above VR1 slope equal to 0. Because above VR1, so V0 equal to VR1 and Vi is less than minus VR2 condition, output voltage equal to minus VR2. So that's why they are the two conditions. And next one, this is the clipping by using clipping circuits, two-level clipping. Same one, another one clipping circuits by using another one. You have to see this one. Clipping circuits, transfer characteristic curve. Here will be two positive reference voltages. Two reference voltages will be positive voltages. Then what is the transfer characteristic curve and output waveform? And again will be three conditions. In the two independent levels, two reference voltages and three conditions will become. So what are the three conditions? So one condition is less than, Vi is less than VR2 condition. Vi is in between VR2 to VR1. And third condition is Vi greater than VR1 condition. So these three conditions, what are the diode status? On or off condition and output voltage. According to this one, for the transfer characteristic curve. Similarly, another one, there will be two negative reference voltages. You are applying input is sinusoidal waveform. Then what is the transfer characteristic curve and what is the output waveform? So generally important one is one reference voltage is positive voltage, another one is negative reference. So this is the right for external examination. Clipping at two independent levels means you have to draw this one and you have to explain these three conditions, input and output waveforms and transfer characteristic curve. You have to explain, you have to draw it. And next one, This is the reference voltage, positive reference voltage, and these are the two negative reference voltages. And next one, the same clipping operation will be done by using Zener diode also, single Zener diode and multiple Zener diodes, two diodes also. So what is the transfer characteristic and what is the output waveforms? You have to go through this one. Otherwise, I will explain first one. So whenever Vi is less than minus V gamma, that means input voltage is less than minus V gamma, that means negative peak. Then diode will be on condition, in the reverse bias condition, on condition. So once it will be on condition, so now output voltage is nothing but, so V naught equal to minus V gamma. That is the output voltage. Next one, whenever the input voltage lies between minus V gamma to Zener breakdown voltage Vz in between. So diode will be Zener diode will be off condition. So once it will be Zener diode will be off condition, so open circuit, input is transferred to the output. So V naught equal to Vi, slope equal to 1. And third condition, whenever Vi is greater than Vz breakdown voltage, then Zener diode will be breakdowns. Then so the Zener breakdown means V naught equal to Vz, whatever the value of breakdown voltage, same value will be repeats. Similarly, Zener diode will be reverse bias direction, and two Zener diodes how to be using. This is the two Zener diodes you are using, two level clipping. How it will be done? Like a square waveform generation from sinusoidal to square waveform generation. So this waveform will be sinusoidal to square waveform means, so reference voltage will be positive reference and negative reference, both will be same, will be requirement, and this time period you have to reduce. That means frequency is very high, will be required. And up to now you have seen diode will be single level clippers and two level clippers. Single level means single diode you are using, and reference voltage will be 0 or some reference voltage be consumed. And two level clipping circuit means multiple diodes, two diodes and two reference voltage are using for clipping at two independent levels. And another one, by using transistors, this is also another non-linear element. By using transistor also, you can clip the input sinusoidal waveform. This transistor also operating in the switch will be two regions or two non-linear regions. What are the two non-linear regions? So one is a cut off to cut into or cut off to active region. Second one is from active to saturation region. There are the two non-linear regions transistor operating at the switch. In the cutoff condition will be open switch and saturation will be closed switch. In between, active region also will be there, but active region duration has to reduce once in time. So that's why you are using some capacitors. You'll be seeing the later on commutating capacitors. So here will be, you have to see the diagram, transistor clipping circuit diagram. It's a basic diagram. Here will be positive supply voltage, VCC supply voltage. This is the collector ratios RC, base ratios RB are using. Now what is the base current IB? So whenever we diode on condition, so minimum voltage will be required here. Base emitter terminal voltage VB equal to V gamma cut in voltage. So generally for the silicon will be 0.7 volts, for germanium will be 0.3 volts. Now IB is nothing but applying, so KCL. So here input voltage is VI, here voltage is V gamma, because VB voltage between base and emitter terminal voltage is V gamma. So VI minus V gamma by RB. This is the base current. And next one, here will be trans clipping operation you are considering. One of the example waveform is, so previous one any sinusoidal waveform. Now you are considering ramp waveform example. So this ramp waveform be considered, input waveform will be varying from, so below minus 0.1 negative value to increases to positive value. So corresponding ramp waveform we are applying. Now what is the transistor operation? This input voltage applying at the transistor base. Now what is the operation required? So here I am using germanium transistor. So germanium transistor, so will be 0.1 volts. That is nothing but cut in voltage. V gamma value is 0.1. And similarly, 0.3 volts, the transistor going to the saturation. That means input voltage whenever here applying, so 0.1 volts above, the transistor going to the active region. So whenever input voltage is greater than 0.3, transistor going to the saturation. This is a germanium transistor you are using NPN germanium transistor. And next one, here will be what is the saturation voltage VBE sat. So VBE sat means, so minimum voltage will be required, input voltage 0.3 volts, then transistor going to the saturation. That's why VBE sat equal to 0.3 volts. Similarly, when the base current, input base current also will increase slowly. Whenever input voltage increases from cut into going to the active, then after going to saturation, so IB increases. So that means base current will increase. Once the base current increases, automatically collector current, output current also will be increase. So what is the relation between the IB and IC? So we know that beta or HF equal to output current by input current for a common emitter configuration. So IC by IB. So IC equal to beta into IB. So IB increases automatically, IC value also will increase up to from cut-in voltage 0.1 volt to 0.3 volts. So whenever input voltage greater than 0.3 volts, what will happen? So whenever input voltage is greater than 0.3 volts, the base current will increase. Why will the base current will increase? So what is the base current formula? So IB equal to VI minus V gamma by RB. This V gamma is fixed one, 0.3 volts. But input voltage value increases, RB also fixed one. So whenever VI value increases greater than 0.3 volts, the IB value will be increase. But IC value will be constant. That means the saturation current IC will be reached to IC sat. And next coming to the another example for transistor clipping circuits, we are using sinusoidal waveform, input waveform. Then what is the base emitter voltage, which is the VBE, and similarly base current and collector current. Similarly output voltage, output variation with respect to the transistor. Here output waveform I want to see here. This whenever we transistor positive peak condition. So positive peak condition greater than V gamma or VBE, transistor will be on condition and going to the saturation. So saturation means VC sat, low voltage. Between so V gamma to VBE sat, in between transistor operating as a active region. So output voltage will be decreased. Whenever we transfer to off condition, collector voltage is VCC. So whenever input voltage greater than cut-in voltage, transistor going to the active region, so collector terminal voltage will be decreased. Finally going to the saturation. The next one is emitter coupled clipper circuit. So here I am using two transistors. So here I'll be connecting is two transistors will be emitter coupled configuration. So here will be two transistors Q1 and Q2. Here important one is Q1 base you are applying input waveform for NPN transistors. Similar those are NPN transistors. And Q2 base you are applying some fixed supply voltage VBB2. Now how will be selecting VBB2? So whenever input voltage negative peak you are applying at the input side or the base of the Q1, then automatically transistor Q1 going to the cutoff condition, then Q2 will be active condition. Likewise, you are selecting VBB2 at V supply voltage. That means transistor Q2 will be active region. So Q1 will be off condition, Q2 will be on condition because of input bias voltage VBB2. Now entire current, there is a transistor Q2 is on, IC2 is flowing from now base 2 and emitter 2 and coming to the RE ratio. Now RE ratio current I is constant. So this I is equal to IE2 only. IE1 equal to 0 because Q1 transistor off condition when our input is negative B. Now coming to the another condition. Now input voltage increases. Input voltage increases means Q1 going to the cutoff to active condition. So cutoff to active condition, then current is flowing from IC1 to base 1 to IE1. That is the example. Total current previously I equal to 10 milliamperes. That means IE2 equal to 10 milliamperes, that equal to I. In the Q1 is cutoff condition. Now, whenever the input voltage is greater than V gamma, then transistor Q1 going to the active region. Let us example. This IE1 equal to 3 milliamperes. So automatically IE2 will be decreased to 7 milliamperes. So total current IE1 plus IE2 equal to constant, that equal to 10 milliamperes current passing to the rest RE. And next one, Why it will be the 7 milliamperes? Previously here 10 milliamperes, now will be 7 milliamperes. Because this Q1 will be on condition, collected emitter current is flowing. This current IE1 passing to the RE ratio. This drop across the RE ratio voltage opposes to the base emitter voltage of the second transistor. That's why second transistor emitter voltage will be decreased. So next one, whenever input voltage further increases at the base one, Q1 going to the saturation. So Q1 going to saturation current means maximum current is flowing from collector to emitter. So IE1 that equal to 10 milliamperes, the current is passing to RE ratio, but IU2 equal to 0. That means second transit going to the off condition. So likewise, so input is transferred to the output condition. So both are will be active condition. Input is transferred to the output condition. Now you have to see the transfer characteristic curve, case 1 and case 2. What are the case 1 and case 2? So whenever input Vi is negative, so input voltage of the Q1 base is negative, trans Q1 is off, Q2 is on condition. So Q2 is on condition means what is the collector terminal voltage? V0 equal to VCC minus drop across RC. That means VCC minus ICT into RC. This is the output voltage of the second transistor up to input voltage, so less than V gamma. And next one, second case, as Vi increases, that means input voltage of the base one of the Q1 transistor will increase. Then Q1 comes out of cutoff condition. Now both transistors will be carrying current, both are active condition. So the total current passing to RE ratio equal to IC1 plus IC2. This is the IC1 current, this is IC2. Both currents will be coming from RE ratios. Now RE ratio current I equal to IC1 plus IC2. Here will be actual one is IE1 plus IE2. But base currents will be almost negligible. That's why IE1 equal to almost equal to IC1. Similarly IE2 also. IC2. And next one, as Vi increases further, then Q1. So Vi increases further, then common emitter follower base one of the Q1, Q2 going to fixed one, that will going to the cutoff condition Q2. So once will be Q2 going to cutoff condition, Q1 will be on condition, then output voltage of the Q2 transistor is V0 equal to VCC. Now in between Q1 and Q2 will be on condition, active region, slope equal to 1. Now input is transferred in between two reference voltages. That is the two-level clipping circuit. This is the output waveform you have to see here. So two-level waveform. And next one, these are the clipping circuits over. So next one, important one, clamping circuits of the nonlinear shipping. What is meant by clamping? So clampers is nothing but to perform the level shifting operation. That means whatever the input sinusoidal waveform will be there, you have to clamp the above some reference voltage or below some reference voltage, or simply called as addition of DC voltage. So why it will be DC voltage will be added here? So any signal will be combination of AC and DC signal that will be passing to any capacitor coupling circuit. Then capacitor blocks the DC voltage. Now addition of that DC voltage by using these clamping circuits. Now how it will be DC voltage will be added, or it will be insert. That will be again will be two types in there. One is the positive clamper circuit, second one is negative clamper circuit. So go through this example. These are the input waveform. Reference voltage line is 0 volts. Now this is a positive peak and negative peak. Let us example plus 3 volts. This is a minus 3 volts. Now positive clamper circuit, observe this one. Entire negative peak waveform also will be upward direction. Now reference voltage here will be center is 0. Here also will be reference voltage 0 volts. But here will be no negative peak here. 0 volts line below no waveform. That means this negative peaks also bring to the above the 0 volts reference line. And why you call it this is a positive clamper? Here will be average value of the DC voltage 0 volts, but here will be average value of DC level is V volts. That is the difference between input waveform and output waveform. Here important one is wave shaping of the clamping circuits will not change. Only change is addition of DC voltage. Input waveform shape peak to peak value is 2V. Here also will be peak to peak value of the output waveform of the clamping circuit also will be 2V. That is a no change. Only change is DC voltage level. Similarly, negative clamping waveform, you have to observe this one. Here will be average value DC level is 0 volts. Peak to peak value is 2V. Now output waveform of the negative clamping circuit is this is a 0 volts line. Now output waveform lies between 0 to minus 2V maximum in between. That means addition of negative DC voltage. That's why this is called as negative clamper. Or another name also for this one is post to peak clamper. Why you call it as post to peak clamper? So post to peak waveform bring to the 0 volts line below this one. That's why this is called as negative clamper circuit also. Now coming to the circuit, what is the main important points? No change in signal shape, and similarly peak to peak value of the input and output waveform will be same. And next one, this is circuit diagram for negative clamper circuit diagram. So here will be input voltage, capacitor and diode. So for this one, when will be this diode will be forward bias condition. So this is the input waveform. Dotted waveform is input waveform. Now input waveform will be divided into 4 quarter cycles. Total period is capital T. So now I'm going to sing first quarter cycle 0 to capital T by 4. So first quarter cycle input value Vi is greater than 0 until reaching to at small t equal to capital T by 4 maximum value peak value. Within this waveform 0 to capital T by 4, diode will be forward bias condition, act as a short circuit. So once this will act as short circuit means this capacitor will be charging to peak value. The capacitor charging peak value Vc equal to Vm. Vc equal to Vm. Similarly, whenever this capacitor will be charging, then what is the output voltage across the diode? Because this diode in first quarter cycle will be act as a short circuit. So once it will short circuit across the output waveform is 0. That's why output waveform in the first quarter cycle 0 to T by 4 output waveform will be 0. This is important one in the external exam point of view. 0 to T by 4 output waveform will be 0. Capacitor will be charging to input peak value Vc equal to Vm. Now whenever input values will be decreased from the second quarter cycle to fourth quarter cycle, input waveform amplitude will be decreased and increase. Within this one, now output voltage across the diode equal to input voltage minus drop across the capacitor. That means output voltage or diode voltage equal to Vi minus Vc. But Vc equal to Vm, peak value. So why? Because input voltage will be decreased, but capacitor voltage will be fixed value. Why it will be fixed value? Capacitor discharging path is not providing. That means across the diode, we are not connecting any resistor. So capacitor voltage will be constant voltage Vc or Vm. So that's why across the diode voltage V0 equal to Vi minus Vc or Vm. So according to this one, you have to substitute the different values of Vi. Suppose Vi equal to 0, then V0 equal to minus Vm. Similarly, input voltage Vi equal to Vm. So Vm minus Vm 0. Similarly, Vi equal to minus Vm, output voltage equal to minus Vm. So likewise, output waveform you have to draw it. This is the negative clamper circuit. Why? Because this average DC voltage value is 0 volts line, but here will be DC voltage value is minus Vm. That's why this is called as negative clamping circuit, or otherwise positive peak clamper circuit also. So positive peak waveform bring back to the 0 volts reference line below. That's why this is called as positive peak clamping circuit. Similarly, modified clamping circuit. Previously I told that capacitor voltage equal to Vc equal to Vm, that is the constant one, because no discharging path will be there. Now whenever discharging path you are providing a resistor, so in the input voltage less than the capacitor voltage, then capacitor has to discharge through resistor. Then output waveform, how to the variation, you have to see this one. And next one, positive clamper circuit or negative peak clamper circuit. So previous circuit and this circuit, what is the difference you have to see. Here will be diode in forward bias direction. So here will be diode will be reverse bias direction. Now, when will be this diode will be on condition, then circuit will be closed condition, capacitor will be charged. Diode into reverse bias means input is negative peak will be required. So negative peak will be starting from third quarter cycle. That is a capital T by 2 to 3T by 4. Within this one third quarter cycle, diode will be on condition. Up to, you have to see here, up to third quarter cycle, output waveform will be 0. Because diode will be open circuit. Now output waveform will be 0. Whenever diode will be on condition, now capacitor will be charging. This is the on condition, capacitor will be charging. The value is capacitor will be negative peak voltage starting from 0 to minus Vm. Now capacitor voltage Vc equal to minus Vm. Now output voltage across the capacitor, across the diode equal to V0 equal to input voltage minus drop across capacitor. So input voltage Vi minus Vc, but Vc value equal to minus Vm. That's why output voltage equal to Vi plus Vm. Now substitute the different values of input voltage. Suppose Vi equal to 0, V0 equal to Vm. Whenever Vi equal to Vm, so V0 equal to 2 Vm. Observe this one. Whenever input voltage Vm, then output voltage value is 2Vm. Likewise, output waveform you provide. This is the positive clamper circuit. See the input waveform here, reference voltage 0 volt sign. Here reference voltage Vm. Now this is called as negative peak clamper also. Why? Because here input waveform negative peak will be bring to the above 0 volts reference line. This is the negative peak clamper circuit. This is the modified negative peak clamper circuit. And one more thing also, biasing clamper. Biasing clamper means you are adding some reference voltage here. Here reference voltage will be 0. Now you are adding some reference voltage here. That is the biasing clamping circuits. And next one, taking the diode and source resistance will be considered. So what is the equivalent circuit? Source resistance RS will be considered. So what is the clamping circuit? You have to see this is the diagram, clamping circuit diagram. This diagram. Within this diagram, source resistance and diode resistance and load resistance are also considered. Then what is the equivalent circuit? Now input source resistance RS will be added here, and similarly here one more resistor, modified clamping circuit. You have seen one more resistor here. Now diode will be forward bias condition RF resistor, in the reverse bias resistor condition RR. Likewise equivalent circuits. So that is the circuit you have to see in this one. Clamping circuit, taking the source and diode resistance will be considered. Then this is the equivalent diagram. So for this diagram, input is positive peak, forward bias condition, forward bias current IF is flowing through the circuit. Again, the same circuit will be redrawn here, and diode forward bias condition here will be RF resistance. So RF is small value 10 to 100 ohms, R is kilo ohms. So these two parallel combination resultant resistance is RF. That's why R parallel with RF, that equal to RF. Now output voltage taken across the diode or RF. Similarly, whenever input voltage is negative peak you are applying, this diode will be reverse bias condition. Reverse bias condition RR resistance. So RR is very large value compared with R. Now parallel combination of these two is nothing but less resistance value R. So that is the reverse bias condition or the equivalent circuit. Reverse bias current IR current is flowing. So for this condition, this is the output waveform rating. This is the output waveform for the positive peak interval. Square waveform you can see here input waveform, positive peak interval output waveform. Similarly, negative peak case. And next one, another important one, clamping circuit theorem. This is a very important one. So clamping circuit theorem says that any input waveform, either square waveform or sinusoidal waveform or any waveform, so ratio of the area under the output voltage in the forward direction to the area under the output voltage curve in the reverse direction is equal to RF by R. RF means diode forward resistance, R means whatever the parallel resistance. This is the diode parallel resistance R. Now for this one, in the forward bias condition 0 to capital T1 interval, positive peak you are applying, diode is forward bias. This is the equivalent circuit diagram. This equivalent circuit diagram, IF equal to input voltage VF by RF. This output voltage here calculating IF equal to VF of TV. That means diode forward voltage divided by RF. So now capacity gain will be the charge gain. So the charge gain formula equal to Q equal to integral of I of t dt. So now I of t means IF of t. What is IF of t? VF of t by R. You have to substitute it. Now RF is nothing but constant value. Take outside the integration. So 0 to T1 interval, positive peak interval, integral of VF of t, output voltage equation. This is nothing but area under the output waveform under the forward direction. That area equal to AF by RF. Similarly, whenever input is negative peak, that means capital T1 to T1 plus T2 interval. So now capacity will be discharged. That means charge will be lost. The charge lost IR equal to equation equal to VR by R. According to this one, charge lost equal to integral of T1 to T1 plus T2 interval. IR of t dt equal to 1 by R. Integral of VR of t dt. This integral of VR of t dt equal to reverse bias condition output waveform area. So now will be under the steady state conditions. So both will be equal. That means charge gain equal to charge loss. That equate and find out the relation AF by AR equal to RF by R. This is a clamping circuit theorem. Similarly, another one, practical clamping circuit theorem also you have to go through this one. And effect of diode characteristics. This is the applications of the nonlinear shaping, clipping circuits and clamping circuit. Clipping circuit means two-level clipping. Sine waveform is converted into square waveform. And clamping circuits are using the television receivers and staircase waveform generation. These are the applications. You have to go through this one. These are the some of the important questions in this unit, and refer the previous old question papers for the problems. These are the theory questions I have mentioned here. This is the completion of second unit. So now I am moving to the third unit. So third unit I will explain only switching characteristics. So another 5 or 10 minutes, this will finish. So third unit actually mainly two parts are there. So one is the diode and transistor switching times, and second one is bistable multivibrators. So this is the third unit. So this is the third unit part. So switching characteristics of the device, diode, and similarly transistor, and design of a transistor switch. And second part is bistable multivibrators. So now I'm going to the diode. Generally will be diodes and transistors will be non-linear device. This you are using as a switch application. So when you are applying switching operation, so diode will be off condition whenever input will be reverse bias voltage you are applying. Similarly, input is forward bias condition, diode act as a closer switch. There is a cut off to on state or on to off state. So whenever similarly transistor also be operating as a two nonlinear regions. One is a cutoff to active, one is a nonlinear region. Similarly, another nonlinear region is active to saturation. So here I'm considering first one is diode as switch. So this is the diode as open switch whenever it will be ideal condition. So forward bias condition, diode can be used as a switch operation. So forward bias condition, diode can be used as a on state. Likewise, ideal diode forward resistance you are assuming is 0 and V gamma also be 0 will be considered. Similarly, whenever diode will be reverse bias condition, see this diagram, and in the reverse bias condition, diode will be open switch. In the forward bias condition, this is a positive voltage. This is a negative voltage you are applying across the diode. Similarly, in the silicon diode practical case, resistance will be neglected. RF equal to 0, V gamma equal to 0.7 will be considered in the positive voltage. Similarly, in the reverse bias voltage you are applying, the silicon diode also will be open switch because the reverse bias case also high resistance. These are the ideal diode, already you know that. And this is the important one, piecewise linear diode characteristics. This is the large engineering applications. So what is the piecewise linear diode characteristics? Whenever we large signal approximation conditions, generally VI characteristic graph of the PN diode is non-linear one. But you are assuming here large engineering voltage applications, this waveform VI characteristic graph you are assuming is a linear one and slope equal to 1 by RF you are assuming. So breakdown voltage or cut-in voltage V gamma, that is called as threshold voltage. So whenever we input voltage less than V gamma, this will be output voltage will be 0. Whenever input voltage is greater than V gamma, then will be diode will be on condition. There is a incremental resistance dV by di. These are the some of the germanium diode and silicon diode cut-in voltage and forward bias condition and whatever the forward bias condition resistance values. And important one, diode switching times and transistor switching times. So what is the diode forward recovery time? So diode forward recovery time is nothing but time difference between 10% of diode voltage from starting position to time taken to attain 10% of final value of the given step input. So starting from 10% of the voltage to starting point to until reaching the maximum and going to the down to 10% of the final value. Within this time difference is called as diode forward recovery time. So VF is nothing but diode forward voltage you are applying, this one. So current waveform you are applying. So this overshoot will be large overshoot will comes because of when will be suddenly input current will be increased across the diode. So this overshoot will comes. Large currents you are applying, this combination is nothing but RL circuit. This diode act as a RL circuit. So when will be low currents you are applying, the step voltage, step current will be low values. This is a parallel RC combination. So intermediate currents you are applying, then the RLC circuit, then the oscillation will be done. This is the forward recovery time and reverse recovery time. And what is the reverse recovery time? Then whenever input is suddenly changed to forward bias to reverse bias, you have to see this one. Input voltage up to 0 to T1. This is a forward bias condition. IF equal to VF by RL. So whenever input is suddenly falling at T equal to capital T1, fall into negative voltage. Then current also will be minus VR by RL. So that is a diode reverse recovery time. So input is suddenly changed to forward bias voltage to reverse bias voltage. Then minority charge carriers, how to be variation? You have to see these diagrams from the minority charge carriers. How to be variation? This is p side minority carriers are electrons. How to be junction will disappear in the reverse bias condition. Similarly, n side will be how it will be disappear at the junction. Similarly, in the forward bias condition, how it will be minority carriers will be increases at the junction. And next one, now according to this one, so what is the diode reverse recovery? When a reverse voltage minus VR is applied at T equal to capital T1 or small t1, the diode becomes reverse bias, and then reverse current minus IR equal to minus VR by RL. This you have to see this minus VR by RL current. And what is meant by storage time? So input is suddenly changing at T equal to T1, positive voltage, negative voltage, but this current will be cannot be discharged instantaneously. Why? Because here minority charge carriers, excess carrier density is available at the junction. So these carriers will disappear, it will take certain time. So that time is called as storage time. Then after, what is the transition time? So transition time is nothing but, see this one. So storage time and this time, what are the discharging time? Is called as transition time. And next one, trans will be what is the regions will be operated. So one is the cutoff condition. Input side is both emitter and base will be reverse bias. Similarly, collector and base junction also will be reverse bias condition. Active region means base emitter junction is forward bias condition. Collector and base junction will be reverse bias condition. Saturation condition, both input side and output side both will be forward bias condition. Base emitter junction and collector and base junction will be forward bias condition. This everybody knows transistor with 3 regions operated. In the active region will be amplifier also. Next one, what is the switch? How it will operates? So whenever input voltage so less than V gamma, so IV equal to 0. So IV equal to 0, this part is called as cutoff region. So whenever input voltage will be increased, so IB value is greater than 0, then transfer going to the active condition. So within the active condition, then will be transfer on condition from collector to emitter, current is flowing on condition. This part is called as active region. Whenever input voltage increases further, IB also increases. IB equal to IB sat. That is the minimum saturation current will be required at the base station, base of the transistor. Then transistor enter into the saturation. Once it will be going to the transistor, we enter into the saturation. IC sat will be fixed to 1, but input base current will be increase. Now you draw a load line. This is the load line will be the DC load line cutoff point, and this point is called a saturation point. And next one, another important one. What is the transistor switching time? This is another important questions. So transistor switching times will be again different types: delay time, rise time, and turn on time, and storage and fall and turn off time. So what is the delay time? This is a common element configuration. So here will be this is the input voltage waveform. Simple example, one pulse waveform we are applying here. So this is the point at T equal to 0 point. So T equal to 0 minus input voltage negative voltage. That level is minus V1. So this level transfer will be cutoff condition. Once it will be cutoff condition, IB 0. So entire thing value will be 0. IB equal to 0, IC also will be 0. Because IB and IC are related. IC equal to beta into IB. So IB 0 means automatically IC also will be 0. Now you are drawing here output waveform. This is the input voltage waveform. This is output current waveform with respect to time. Now whenever input voltage value will be increase, input waveform at T equal to 0 point, suddenly increase to V2 voltage. But base current will not be increased immediately. Similarly, collector current also will not be increased immediately. You are observing here collector current will not be increased. IC also will be 0. So why it will be 0 up to certain time? That we will discuss later. And what is the delay time? So delay time means the time required collector waveform to reach from 0 to 10% of collector saturation current. That means maximum current. So the duration of time is called as a delay time. 0 to 10% of collector current. That is a 0.1 IC set. This duration of time, collector current will be increased. The duration of time is called as delay time. Similarly, rise time is 10 to 90% of the collector current increases. The duration of time is called as rise time. Similarly, what is the turn on time? So delay time plus rise time is called as turn on time. And next one, what is the storage time? Storage time means input will be reverse here. Let us example T equal to capital T1. So input will be reverse at this time up to, and collector current will be reaching to 90%. This duration of time is called as storage time. That means input will be state will be changes at this point to collector current will be decreased to 90% of the maximum saturation current. The duration of time is nothing but storage time. Similarly, fall time means collector current will be decreased from 90 to 10% of collector saturation current. This is the fall time. Now T off time means turn on time means so storage time plus fall time. These are the transfer switching characteristics. And why I already told that. So why will be delay time will be increased? Collector current is not increased. When our input is applying at T equal to 0, but collector current is not increases immediately. These are the three regions. So driving signal, input signal applied at the transfer base. A non-zero time is required to charge up the junction capacitance. That means base emitter junction also junction capacitance will be exist. So this capacitor will be charges. It will require some time. So that's why input you are applying at the T equal to 0, collector current will not appear. Second one, so emitter junction to this will be emitter to base to collector. It is reaching some time delay, and a non-zero time will be required to rise from 0 to 10%. These are the three regions why it will be delay time will be required. Next one, design of a transfer switch. So the design of transfer switch, this is the same common emitter configuration. Here one more capacitor will be inserted here. Why it will be this capacitor and this biasing voltage will be providing here? So this capacitor or biasing voltage provided because transistor operating in this switch operation, the cutoff means open switch, in the saturation closed switch. Now in between active region transistor operating in the amplifier. This active region transition width has to reduce. That's why this capacitor and supply voltage are using it. So here input voltage two levels, V of 0 and V of 1. V of 0 means low voltage level. That means transistor will be cut off condition. When our input is V of 1, transistor will be saturation condition. Now here we will explain whenever VA is V of 0. That means input is lower level. So lower level means transistor will be cut off condition. So transistor is cut off condition means collector terminal voltage equal to V naught equal to VCC. That is high. So input is low, output is high. Similarly, input is higher level, VA equal to V1. So transistor going to the saturation. Then output equal to VC sat. So VC sat means almost equal to 0. That means lower level. That means input is low means output is high. Input is high will be given, output is low. That's why the transistor is called as inverter or not gate. And in this operation, you have to find out what is the base voltage, VB, base emitter terminal voltage, this VB value, this node voltage. So VB equal to this potential voltage equal to minus VBB into opposite resistance R1 by R1 plus R2. Input voltage V of 0. V of 0 into opposite resistance R2 by R1 plus R2. But V of 0 value, I am assuming his input is lower level 0. That means VB equal to minus VBB into R1 by R1 plus R2. That means cutoff condition, whenever input is lower level, transistor will be cutoff condition, VB is negative voltage. You have to see here VB value is minus VB into R1 by R1 plus R2. Negative voltage transistor will be cutoff condition. Similarly, whenever input is Vi equal to V1, then transistor going to the saturation condition. This is sufficient base current is available, sufficient base voltage providing here, transistor going to saturation. So within this condition, what is IC bar? So IC is nothing but this current. This current IC equal to VCC minus VC sat by RC. And IB minimum equal to IC by HFE. We know that relation between beta or HF equal to IC by output current by input current IB. So now here IB minimum equal to IC by HFE minimum. And now I1, this current is, I am assuming R1 resistor current is I1. So I1 equal to V1, that means input step voltage V1. This voltage VB is at, so V1 minus VB is at by this resistance R1. This is the I1 current. And this current I is assuming is R2 current is I2. So I2 equal to VB is at minus of minus VB by R2. So now how much base current is flowing here? This current is I1, this current is I2. So I1 current is entering, I2 is leaving. So IB equal to I1 minus I2. So IB equal to I1 minus I2. Now this IB equal to IC by HF. So this one we are using, and find out the R1, R2 values and RC values by using the transistor design. This is the completion of this third unit, first part. The students now will be asked any doubts will be there regarding first unit, second unit and third unit up to this one. Hello.